Hello, dear students. Welcome to the channel and welcome to the playlist of transmission line modeling and performance. In this playlist, we are discussing about the modeling and performance of transmission line in detail. So, initially, we have seen what is a transmission line. We have seen different types of transmission line. We have gone through short, medium, and long transmission lines, and then we had a detailed discussion of short and medium transmission lines. And in medium transmission line, uh, we had two different analogies or two different methods to represent a transmission line, which were called nominal t and nominal pi representations. And for all these type of representations and all this type of lines, we have derived the abcd parameters, which are also known as generalized constants for your transmission line. So uh, that's what we have done in this lecture series up until now. Today we are going to discuss about the long transmission lines, and we are again going to discuss about long transmission line in detail, and we are going to see a method which is called rigorous method, or it is generally a method which is used for analysis of long transmission line, but it has a name. It is called rigorous method. So uh, before I start the video, if you haven't checked out the previous videos or the very last videos of this playlist, so please check it out. The link will be flashing on the I button on the top right hand side corner of your screens. So if you haven't, please go and watch it if you want to learn in detail about the power system, and especially uh, for the calculation of transmission line modeling and performance part. So it will be very helpful to you. And except that, there is one thing I must mention before starting this video, that to understand this concept, to understand long transmission line, first you must have some idea about transmission line. You must have some idea about what is power system, what are its components, uh, how what are the components of power system, how transmission, distribution, or generation takes place. So about that, we have done a detailed discussion in one separate playlist. So if you are interested, if you want to know more about the general principles of power system, if you want to know the learn the basics of power system, you can find that playlist in the description below. So if you want to know about it, please go and check that playlist out. But if you have already, let's get started with the long transmission lines. So firstly, what lines do we call long transmission lines? Normally, the lines which have length more than 160 kilometers are considered to be long transmission lines. But it's not necessary that always a line greater than 160 kilometer will considered a long transmission line. Different books have different definitions for the very same thing. So there is no compulsion, there is no standard, but in general case in India, we take a line, we consider a line as a long transmission line if its length is more than 160 kilometers. Now for such length of lines, the line which are longer than 160 kilometers, what happens? The parameters, line parameters, are not lumped, right? What do? We distribute the line parameters uniformly along the whole length of my transmission line. And because this uniform distribution of line parameter, what will happen? The voltage and current will be different from point each and every point, right? So if at one point I'm having different voltage, and so other point I will be having different voltage. Same, if I'm having different, I'm having a current I1 at this point, then I will have some different current IN at this point, right? So now you all know that line constant of the transmission line are uniformly distributed. The same thing was there for nominal T, nominal pi, I mean medium transmission lines, right, over the entire length of your line. So in nominal T and nominal pi, what did we do? We took two different parts, right, for your line constants for shunt admittance, right? And dependent on that, we called it either nominal T or nominal pi method based on the distribution of your either you can call it on the basis of distribution of shunt admittance, or you can call it distribution based on the line parameters, right? So that's what used to happen for nominal T and nominal pi. But here what is happening, this uh, line constants are uniformly distributed over the entire length of your line, right? But the reasonable accuracy can be obtained in the line calculation for only short and medium lines by considering them as constants or lumped, right? So uh, when you when we take that assumption, when we assume that the line constants are lumped, uh, we and by after assuming that, when we try to calculate all the parameters things for long transmission lines, which are normally greater than larger than 160 kilometers, we cannot find uh, the exact value. I mean the values we will find will have some serious errors, right, in the performance calculations only. So in order to obtain fair degree of accuracy in performance calculation of my um, long transmission lines, the line constants are considered uniformly distributed throughout the entire length of my line. And when we do that, when we uh, consider the line constants uniformly distributed throughout the entire length of my line, this method will be called rigorous method or rigorous treatment, uh, which we use for the solution of such lines. Okay, so now let's come to figure. Let's see this image figure here. So what is it showing? It is showing the uh, equivalent circuit of three-phase long transmission line uh, on a phase neutral basis. So the whole line length is divided into n sections, as you can see here, and you can see there are n number of sections in which my line has been distributed or divided. And here what are we doing, that for all my whole my line, we are taking some points in consideration. So let me show you those points. After reading that point, I will be shuffling between slides so that you can understand it better. So come here and see what is the first point. So the first point is the line constants are uniformly distributed over the entire length of my line, as it is actually is, right? So first point which we consider is actually not only a point, it is a fact. It is not an assumption like we took in short and medium transmission line. It is actually fact that the line constants are uniformly distributed over the entire length of line, and that is actually the case. The second thing is the resistance and inductive reactances are in the series. Okay, they are series elements. So as you can see here, see, we are having resistance here, we are having inductive element here, and both of them are in series, right? Now see what is the third point. So the third point says the leakage susceptance, which is given as B here, and the leakage conductor, which is given as G here, see, are the shunt elements. Okay, and the leakage susceptance is due to the fact that capacitor exists between the line and my neutral. So here you can see the capacitor, and it is between the line and neutral. And again, same way as the leakage conductance, this G, it takes into account the energy loss which occurred through the uh, what you call leakage over the insulator, right? Or there is an effect which is called corona effect. uh, don't worry, it's not related to COVID, but there is a corona effect in my high voltage AC lines. And uh, because of that, uh, we see an additional ozone layer or ozone layer and some hissing noise towards the conductor on close to the conductor. So uh, this corona effect and uh, leakage over the my insulation will be dealt by this leakage conductance. Okay, so basically any energy loss, corona is nothing but one type of energy loss. So any energy loss is dealt by this uh, conductance, leakage conductance. Okay, and what will be the value of my admittance? So value of my admittance will be under root of G square plus B square. Okay, and here you can see what is G and what is B. So G is your leakage conductance and B is your leakage susceptance. And fourth and last point is the leakage current throughout the shunt admittance is always maximum at the sending end of the line, and gradually decreases continuously as the receiving end of the circuit is approached. And at that point, at the receiving end of the circuit point, its value will be 0. Okay, so this leakage current through my shunt admittance will be maximum at sending end, which means here, and it will be almost 0 over towards here. Okay, so these are the points which we have to keep in consideration while doing the calculations. So now that we all are clear about it, let's move forward towards the analysis part. So this method which we use for the analysis of long transmission line is also called rigorous method. And in this figure which I've taken courtesy of S. Chand publication, VK Mehta, Rohit Mehta, Principle of Power Systems. So this image which shows a three-phase line with impedance and shunt admittance of my line, and both are uniformly distributed. So what we will do here, first we will consider a small element of line of the length. We will call it dx. So here you can see it is that part is denoted by dotted lines here. See this section, small section, we will consider this part first, and we will call this small portion or small part of the line length will be we will be calling it dx. Okay, and how far is it from the receiving end? So it is at the distance x from my receiving end. Okay, here z will be the series impedance of my line per unit length, and you can find the value of z or z here. Same ways, what will be y will be my shunt admittance of the line per unit length, and you can see y here. What will be v? So v will be the voltage at the end of element towards receiving end. What will be v plus dv? So it will be voltage at the end of element towards sending end, right? And element by element I mean this element, dx element. Okay, what will be the value of I plus di? So it will be current entering the element dx. The current which is entering this element dx will be I plus di, and the current leaving this element is I. See, now let's try to consider for only this small uh, dx portion or this small dx element. So can you tell me what will be the series impedance for this small portion or small element dx? It will be z into dx, right? See, we want to find the impedance and there is nothing except for this impedance, so it will be z into dx. Same ways, when I want to find the shunt admittance, it will be y into dx, because except for y into dx there is no other shunt admittance present, so it will be nothing but y into dx. Okay, now again, see the image and tell me what will the value of dv here. The voltage at the sending side here, and here the voltage at the voltage on the right side, voltage which are close to receiving end and dx. Okay, so based on these two, or by simply taking difference of these two, can't we find the value of dv, right? And we do, what will be the value of dv? The value of dv will be c, how much current is actually leaving my dx, it will be I. Okay, and what is the series impedance? It is z into dx, right? So dv will be equal to I into z into dx. Now let's take this dx portion into the denominator of dv, so we will have dv by dx is equals to iz. Now the current entering element is, we already know, I plus di, whereas current leaving element is I, right? See here, the current entering this element is my element dx will be I plus di, but the current which is leaving my element is nothing but simply I, right? So the difference in the current flow here through my this portion, through my shunt admittance of the element, what it will be? It will be nothing but di, right? Just like the difference we had dv here, here we will have difference di, right? So now we know what will be the difference, right? So let's try to find the value of di here, current through the shunt admittance of my uh, element dx. So you have to find the value of di here. So again, see, how do we find it? Current will be flowing through here, so try to find it will be this voltage v, and multiplied with my shunt admittance y into dx. So my current will be, current through the shunt admittance will be y into dx into v, and taking this dx into denominator, we will have di by dx is equals to v into y. Now differentiating my first equation, this equation, with respect to x, what we will get, d square v by dx square is equals to di by dx into z. Okay, uh, and we all know that what is the value of di by dx here, right? It is v into y. So we will simply substitute the value of di by dx in that formula, so we will have z v into y, d square v by dx square is equals to yz into v. Okay, now when you solve this differential equation, d square v by dx square is equals to yz into v, you will find the value of v, and it will be something like this. So v will be equal to k1 cos h x under root yz plus k2 sin h x under root yz. Okay, now again differentiate this, let's take differentiation of this equation as well with respect to x. So we know what is the value of v. Let's try to take dv by dx. So when you take the dv by dx, as you can see here, it will be k1 root yz. What will be the differentiation of cos h? It will be sin h x root yz plus same ways k2 root yz cos h x root yz. Okay, but we already know what is the value of dv by dx, right? It is nothing but iz. So instead of dv by dx we will write iz here. So here what will happen, iz will be equal to k1 under root yz sin h x root yz plus k2 under root yz cos h x root yz. Now what we will do, we will take this z which is into multiplication with I into the denominator of y. Before doing that, what we will do, we will take this root yz common, we will take this root yz out. So when we take this root yz out, we will have under root y into z, and when we take this z into denominator of under root y into z, the whole z will go into denominator, and the z which went in denominator will have power 1. The z which is in multiple with y will have power 1 by 2. So when you do the subtraction of power, you will be left with 1 by 2 power in denominator. So we will have under root of y by z, because y was already having 1/2 power, right? So we will be left with I is equals to under root of y by z k1 sin h x root yz plus k2 cos h x root yz. Okay, and we will call it equation 5. Now if you have paid attention that this equation 4, and the equation which you derived just now, this equations 4 and 5 are the expressions of v and I in the form of constants k1 and k2. Okay, and now that we have derived the equations for v and I, what we will do, we will try to find the values of k1 and k2. And remember, we have said that the values of current and voltage changes as time progresses, right? So let's try to do one thing. Let's try to consider at x is equals to 0, my v will be, what will be my v will be vr. And see this, at x is equals to 0, v will be vr, because x is 0, right? And what will be my uh, what will be the uh, value of my current I, this I which is coming out from this element, dx element, it will be vir, right? So let's just put these values in the fourth equation, in this equation, and see what we get. So what we get will be vr is equals to k cos h into 0 plus k2 sin h into 0 sin s 0. So you know the value of cos s 0 and sin s 0. So cos s 0 is 1 and sin s 0 is 0. So we will be left with v1 only, k1 only. So what does it means? K1 is equals to my k1 is equals to my vr, right? Now same ways, let's put x is equals to 0, v is equals to vr, and I is equals to ir in this equation, the fifth equation. And when we will do it, we will find the value of ir will be equal to under root of y by z k1 sin s 0 plus k2 cos s 0. So you know the value of sin s 0 is equals to 0, cos s 0 will be equal to 1. So we will be left with under root of y by z 0 plus k2, which means under root of what will be the value of k2? That was the value of ir, right? So what will the value of k2 will be equal to under root of z by y, because we are sending this y by z on the other hand, on the other side. So it will be z by y into my ir. Now we have values of k1 and k2. So what we will do, we will simply substitute these values of k1 and k2 in the equation 4 and 5. So come here, see, this was my equation 4 and this was my equation 5. So we will simply substitute the values of k1 and k2 in the equation 4 and 5. See, so what is the value of k1? K1's value is vr, and what is the value of k2? K2 is under root of z by y into ir. So substitute here, we have v is equals to vr cos h x root yz plus under root z by y into ir sin x under root of y by z. And let's verify what we are getting here. V is equals to vr cos h x under root yz plus under root of z by y ir sin x sin h x under root yz. And what will be the value of I? So I will be equal to under root of this equation, this fifth formula. See this here, you can see this formula. So what will be the value of I is equals to under root of yz. What is the value of k1? K1 is equals to vr, so vr sin h x under root of yz plus what was the value of k2 under root of z by y into ir cos h x under root of yz. So the I value of I will be I is equals to under root of y by z vr sin h x under root yz plus ir cos h x under root yz. Right. Now the sending in voltage vs and the sending in current is are obtained by putting the value of x is equals to l in the equations of voltage and current we have just derived. So let's simply substitute the value of x is equals to l and rewrite our equations. Okay, so when we do that, what will we get? We will simply get vs is equals to vr cos h l under root yz plus under root of z by y ir sin h l under root yz. This will be the value for vs. We did nothing but substituted, we just wrote l instead of x whenever we see x. So we did that, and now come to value of is or I. So what will the value of my is will be equal to under root of y by z vr sin h l under root of yz plus ir cos h l under root of yz. Now see both of these equations carefully and tell me one thing. Can we take the values of l under root of yz and represent it in another way? Because l is outside of my square root. So if I want to put this l into the square root portion, I will have to take 2l's. I mean, I have to take l square, right? So what I will be having, ly into lz, as you can see here, ly into lz. And what will be the value of ly? It will be capital Y. And what will be the value of lz? It will be capital Z. So we will be left with under root of yz, but this time yz will be capital. Okay, now that we have found the value, we have found capital yz, what we will do, we will first consider this case when we were having z and y in numerator and denominator, and we were having square root over it. So what we will do with it this time, again, instead of small yz, we will make it capital yz, because instead of x we can always multiply and divide by l, right? So we just multiplied and divided by l, and we got capital Y divided by capital Z, right? And what will be the capital Y and capital Z? So capital Y will be the total shunt admittance of my whole line, and capital Z will be the total series impedance of my whole line, right? So Y and Z are nothing but impedance and admittance. So simply replace this small yz instead of in place of small yz, let's write the capital yz. So we will have what we will get vs is equals to uh, vr cos h under root of yz plus ir under root of z by y sin h under root of yz. That will be my value of vs. And for is, what we will get is equals to vr under root y by z sin h under root yz plus ir cos h under root yz. Okay, So that will be the value of my sending end voltage and sending end current. And if you don't want to stop here, this is by the way your rigorous method. If you don't want to stop here, if you want to expand the hyperbolic sine cosine function in terms of power series, if you have learned the power series during your calculus classes, so we can represent it with the help of power series. So cos h under root of yz will be equal to 1 plus zy divided by 2 plus z square y square divided by 24, and up to update will go. Same way as you can also represent the sine value. So sine h under root yz will be what it will be. uh, so if you are good with power series and you are good with expansion of power series function, please try to do the sine part, and mention your answers in the comment section below. I will go through your answer and I will tell you if the answers you have came up with are correct or wrong. So we will end this lecture here. If you have any type of doubts or questions related to this subject, particularly this playlist, or anything in general, please feel free to mention it down in the comment section below. If you have any other feedback for me, if you have any suggestion for this channel, or related to the videos I make, all of the feedback, all of the suggestions are always welcome, and I will try to answer your comments as quick as possible and as much as possible. So I will be seeing you in the next lecture of this very same transmission line modeling and performance series. Till then, goodbye, take care everyone, and again thank you very much for listening the lecture.